Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So in this class we'll discuss about the radiation from the current source. So the first case we'll be considering is a jet directed current carrying element. This is a jet directed current carrying element and it is carrying a current of I naught and the length of this current element is very small, TL, infinitesimally small current carrying element which is positioned along the z-axis. That's the usual first dipole people usually consider for the radiation analysis. But what we are going to consider now is a more complicated case where you displace this dipole at a position rds from the origin. So this dipole was along the z-axis and it was positioned at origin, but now we displace it by a position vector rds. And one more thing is that we also change the orientation of this dipole in any arbitrary direction. So that's the second case. And the third case is basically you assume that there is a bulk conductor at a distance rds from the origin and it is having a current density J here. The volume of this bulk conductor is B dash and the current density, volume current density is J for this current which is shown here. So this is a most general case we can consider for finding the fields radiated out of this current density, and the previous two cases, second case and first case, is a particular case of this third case. So in this class we are trying to find the fields radiated by J current density which is located at rds from the origin. So the procedure for finding the fields, radiated fields, boils down to just three steps. And the first step is basically you find the fields from the potential. So I will find the magnetic vector potential from the current density and find the fields. So how do I find magnetic vector potential from the current density? I just take the convolution of the current density with the Green's function for free space. So once I have the magnetic vector potential, I can find the magnetic field by taking curl of magnetic vector potential and multiplying by 1 by mu. That's a very simple step we have here. In the third step, once I have the magnetic field, I can always find the electric field by taking curl of magnetic field and multiplying by 1 by j omega epsilon. So these three steps we are trying to carry out for finding the radiated fields from a current density J. So first thing first, we need to know the coordinates for the source and observation. So this is the XYZ Cartesian coordinate system. Let's say this is the origin, then this is the observation point and this is the source point. The vector from vector O to P, OP, vector from point O to point P, OP is denoted by R hat, and the vector from O to S is denoted by R dash hat. And the difference between this is SP is basically R minus R dash. I will denote the difference between the observation point and the source point as RD, D for the difference. So RD is R minus R dash. So R vector will have coordinates XYZ and source point S R dash will have X dash, Y dash, Z dash. The difference of these two RD vector will be R minus RD. R dash is X minus X dash, Y minus Y dash, Z minus Z dash. So we need to remember that there are two coordinate systems, one for the source which is usually denoted with a dash, so X dash, Y dash, Z dash for the source coordinate. For the observation coordinate we have X, Y, Z without any dash. And these two coordinate systems are independent of each other. And one more point to be noted is that this nebula operator or del is with respect to the observation coordinates. So with this point in mind, let us try to find the fields. Before finding the fields, we first find the potential, magnetic vector potential from the current density. and this is basically convolution of current density with the Green's function for free space, and that's what we have the expression for magnetic vector potential is the convolution of the current density and the Green's function for free space. So I have the magnetic vector potential, then I can find the magnetic field by taking curl of it and multiplying by 1 by mu. So 1 by mu curl of A is the magnetic vector potential. When I take the curl of magnetic vector potential, this curl operator will operate on the integrand of the magnetic vector potential. So integrand is product of vector J and scalar quantity G. So when curl operates on the product of a vector quantity and scalar quantity, I can simply find it as scalar quantity curl of the vector quantity plus gradient of the scalar quantity curl cross product with the vector quantity. So that's a vector identity you have. And so we have first term and second term when I take the curl of the integrand of the magnetic vector potential. So this is the integrand for the magnetic field is curl of product of vector current density with the scalar function G. So now when I take the curl of a product of a vector quantity and scalar quantity, I get two terms here, the first term and second term. Looking at the first term, this term inside the second bracket, curl of J R dash. Curl is an operator in the observation coordinate, whereas J R dash is for the source coordinate. So they're independent, so this curl will become simply 0. So in order to find this integrand here, we just need to find this second term here. But in order to find the second term, I need to first find gradient of G. So you can find it, you know the expression for G. G was having this expression you have here. So now in this expression, if I put RD is equal to modulus of R minus R dash, that's the distance between the source and observation point, I can simplify the expression for G as this here. G is simplified. What you need to notice here is that G is actually having two terms which are dependent on RD. So this exponential term is dependent on RD. This 1 by RD is also dependent on RD. So when I take the gradient will operate on this, multiply with this, plus gradient will operate on this, multiply with this. So let us try to find the result when I operate gradient on this exponential function or to this 1 by RD term. Just before that, we need to just remember what was gradient. Gradient was simply this here, dou by dou x, x hat, plus dou by dou y hat, plus dou by dou z, z hat. What was RD? RD was the distance between the source and observation point. It was square root of x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square. So I have del, I have RD, I can find out what will be the reason when del operator operates on 1 by RD. That will be minus 1 by RD square RD hat. When del operates on exponential minus j beta RD, it will be minus j beta exponential minus j beta RD RD hat. What is RD hat? RD hat is the unit vector along the direction of RD vector. So RD hat is R minus R dash by modulus of R minus R dash. RD vector can be written as its amplitude is represented by RD and vector direction is represented by RD hat. So the final expression we have for the gradient of G is this, and here this is RD hat here. So now if I take out RD from this first bracket here, that's what we are doing in here. If I take out RD from this first bracket term here, then RD will come out, then so we need to divide by RD here, so this term will become RD cube RD square here. This first term will become RD cube and second term will become RD square. So this term here you see it is RD hat, this is the RD vector. So the expression you have for the gradient of G will be like this with the RD vector here. So we have the second term. Second term is basically gradient of G cross product with JR. So this is gradient of G. You do cross product with JR dash, you get this integrand of the magnetic field. So we can write down the expression for magnetic field now. Magnetic field can be expressed as this expression you have here. This is the integrand we have derived, and we'll integrate this over the volume B dash and multiply by 1 by 4 pi. Then we get the magnetic fields. I will make a simpler expression for this magnetic field by assuming, look at this term here. This term here is a scalar quantity, but this term here is a vector quantity. So I represent this scalar quantity by a scalar A and vector quantity, this vector quantity by another vector B. Then I can simply write magnetic field as 1 by 4 pi integration over the volume B dash product of scalar quantity A with vector quantity B. So this is a very simple expression we have for the magnetic field. So second step is done. We have got the magnetic field expression. The third step is find the electric field from the magnetic field. I can simply find the electric field from magnetic field by taking curl of it and multiplying by 1 by j omega epsilon. So when I take curl of the magnetic field, this curl will operate on the integrand of the magnetic field, which is basically product of A scalar quantity with B vector quantity. So this curl will operate on this product of a scalar quantity and vector quantity. So we want to find this integrand here for the electric field expression. We can apply the vector identity curl of product of a vector quantity with a scalar quantity, simply scalar quantity curl of the vector quantity plus gradient of the scalar quantity cross product with the vector quantity. So if I want to find this integrand here, I have two terms, first term and second term. Let us try to find the second term first. So in order to find the second term, which has a gradient of A here, I know what is the expression for A. So I plug in the expression of A here. Here in the expression for A, I have a product of two functions. One is exponential, another is inside this first bracket. So del will operate on exponential function and multiply with this function inside the bracket, and plus del will operate on this function inside the first bracket and multiply with exponential j beta rd. So when we do that, we have the expression for the gradient of A. This expression you have here. Once I have gradient of A, I want to find the second term. Second term is cross product of gradient of A with the B vector. So this is the B vector. B vector is cross product of RD vector with the J vector. So B vector is cross product of the RD vector with the J vector, and this is the gradient of A we have here. So can we simplify it? You can replace this RD vector by RD hat. RD is the amplitude of the RD vector, RD hat is the direction of the RD vector. So this RD here and this RD square, you can cancel it out. So the final expression is like this. We have the second term of the integrand of the electric field expression. Let us find the first term of the integrand of the electric field expression. That is curl of B. It has a term curl of B. See, in the second expression, first expression, we have curl of B into A. So if I want to find curl of B, what was B? B was RD cross product with J. So here it's basically you are taking the curl of a cross product of two vectors. You can use the vector identity and it will have four terms. First is J dot del RD, J del dot RD, RD dot del J plus RD del dot J. These are the four terms you have for the cross product, curl of a cross product of two vectors. Let us try to find this four terms. First term, let us try to find the first term. First term is j dot del. What is j dot del? J is a vector, any arbitrary vector in the xyz region. It will have component jx, jy, jz, and del operator was having del by del x, x hat, del by del y, y hat, del by del z, z hat. When you do dot product of these two, what you get is jx del by del x plus jy del by del y plus zz del by del z. So now when this del by del x operate on this vector here, only this one will be dependent on the x variable, so we get a, this will be differentiated, others will become 0. When del by del y operate on this, only this term will be differentiated, all others will be 0. When del by del z operate on this, only this third term will be differentiated, other terms will become 0. Finally, what you are getting is the vector j itself. Let's look at the second term. Second term is minus j del dot rd. What is del? Del is del by del x of x hat, del by del y of y hat, plus z del hat del by del z. What is rd? Rd is the distance between the source and observation. So when this operate on this function here, you will get 3. You will get 3. This and this 1, this and this 2, this and this 3. There should be a dot here, dot product of these two vectors. So you get a 3, so minus 3 jr dash. How about the third term? Third term is minus rd dot del jr. So rd dot del is this and jr is this. Jr is any arbitrary current density existing in the xyz region, and when you differentiate it with respect to del by del x, del by del y, del by del z, it should be equal to 0. Similarly, the fourth term is divergence of jr dash, but this del operator is totally dependent on xyz coordinates, whereas this jr dash is totally dependent on x dash, y dash, and z dash, so this will become 0. Finally, what we have is curl of B is simply minus 2jr dash. So we can find out the first term of the integrand of the electric field. A curl of B is, you substitute the scalar quantity A, and curl of B is minus 2j. So this is the expression you have. We have first term and second term of the integrand of the electric field, so we can find the expression for the electric field now. This is the integrand of the electric field expression you have. So integrand is curl of A scalar quantity B vector. This is what we have already find out. So we can just plug it in here and we have the expression for electric field. This long expression you have here. So you don't need to worry about this long expression here. What we are interested is in the far field of region of the fields which are in the far field regions of the antenna, and those are actually the usable fields for long distance communication. Most of the time we use these far fields for wireless communication, mobile communications. So the condition for the far field is the field variation with respect to 1 RD should be 1 by RD. So we can neglect all the higher order terms. For example, if I want to find the magnetic field in the far field, I just don't need to worry about this 1 by RD squared term. I just need to worry about 1 by R term here. So the expression for magnetic field will be very simple here. We just have one term. Similarly, expression for the electric field also, we just need to worry about the term which is dependent on 1 by RD, which is this term here. All of the terms are 0. So this term is 0, this term is 0, this term is 0, this term is 0 in the far field, because the variation of field is, here is 1 by RD square, 1 by RD cube, so 1 by RD cube and 1 by RD square. We can neglect it, so we have only one term for the electric field in the far field. This simple expression you have here. Okay, so we have neglected the higher order terms, but we also need to further approximate the relation we have in the far field by considering the this diagram here. From here you can find out the relation. For example, I have RD head. RD head I can now approximate as R head, because we are in a region which is very far away from the source, and the contribution from this RDS is negligible. So now in the expression for the far fields of the current density we have considered, we have a term like 1 by RD exponential minus j beta RD. So what happens to this term? So for the amplitude term, since you are very far away distance, 1 by RD will be approximately 1 by R. But for the phase term, you need to also consider one term. You cannot just simply write this as exponential minus j beta r. The contribution from the RDS portion is also not negligible because phase is varying from 0 to pi, but r is varying from 0 to infinity. So when you are at very far away distance from the source, 1 by rd can be approximated by 1 by r, but exponential term you need to add one more term. So this is the additional term you need to have. You need to subtract r minus r dash dot r head. What is this term here? This term here, you look at this diagram here, you take a projection of this r dash along the r head direction. This is the r head direction. You take a projection here. How much is this length here? This length is basically r dash dot r head. This is projection of r dash vector along the r vector. You need to subtract this from the r. Then only you can find this exponential term here. So we have everything. We can write down the expression for the far fields of the magnetic field. This will be like this. Once we have the far field of the magnetic field, we can also find the far field of the electric field. It will also be simplified like this. We have a very simple expression now. So first thing you need to notice here is that magnetic field. In the magnetic field expression you have r cross. See, magnetic field expression you have here r cross of some vector j. So obviously magnetic field will be perpendicular to the r direction, radial direction, because we are doing r cross with another vector, so magnetic field should be perpendicular to the r also. Magnetic field is perpendicular to the radial direction. You can also find out the relation between electric field and magnetic field. We have the expression for electric field and magnetic field. If you closely look, electric field is simply square root of mu by epsilon, cross product of magnetic field with the radial vector r. So what is this square root of mu by epsilon? People usually call it as wave impedance, and it is around 367 for the free space. For the free space, wave impedance is eta naught, and we can find it as square root of mu naught by epsilon naught. Everybody knows what is mu naught and epsilon naught for free space. You can plug it in and it comes out to be around 367 ohm. So that's a wave impedance for the free space. So from this relation, what you can observe is that electric field is a larger quantity, magnetic field is a very small quantity. And one more thing is that electric field is perpendicular to the magnetic field because this is the cross product of magnetic field with radial direction, and it's also perpendicular to the direction of wave propagation, which is along the radial direction. One more thing you can observe from this expression is here is exponential minus j beta. This is a wave propagating along the positive radial direction away from the source. So now the derivation we have done for the electric field and magnetic field was for any arbitrary current density in the XYZ region. And in many cases, people start radiation analysis, field analysis of radiated waves by considering a small current carrying element which is infinitesimally small. People call it Hertz dipole. So now let's say if you consider this is the XYZ coordinate system, I consider a small current carrying element carrying a current I naught and length dl, which is arbitrarily oriented along the d head direction. I can easily find it now because I have done it for the any arbitrary current density. So the expression you have can be deduced for this Hertz dipole, a small current carrying element of length dl and carrying a current of I naught. So we have the expression for magnetic field like this. That was for the any current density J. So beta r dash dot r head can be also approximated as 1 in this case. So in that case, we can express this whole integral here as simply what is J now? J is I naught and dV dash will become dl, and what is the direction of the current? D head. So this whole term can be replaced by I naught dl d dash now. So the magnetic field will become now simply this term here and cross product of r head with the d hat vector. So this for any arbitrary direction along the d direction. So this is the far field of an arbitrarily oriented current carrying element. This is a magnetic field. Once you have the magnetic field, you can find the electric field by doing the cross product of magnetic field with the radial unit vector r hat multiplying by eta. So we have the expression for electric field. So this was for any arbitrarily oriented current carrying element. Let's say if you want to find it for the popular cases where you have a vertical electric dipole or horizontal electric dipole, let's see that. Just before that, we need to know coordinate transformation for finding the fields for VED and ICD later on. So let's see what is coordinate transformation. So this diagram will show the relation between the spherical and the Cartesian coordinate system. XYZ is the Cartesian coordinate system. This is R here for the first coordinate for the spherical coordinate system, and the angle it makes with the z-axis is theta. Second coordinate for the spherical coordinate system, you take a projection of r in the xy plane, find this angle this projection makes with the x-axis, that's phi. R theta phi are the coordinates for the spherical coordinate system. And let's look at the unit vectors. This is the radial unit vector along the radial direction r hat, and theta is perpendicular to this radial unit vector. Theta is along this direction. Phi is perpendicular to both r and theta and is in the xy plane. So you need to remember all these things for the coordinate relations between the spherical and the Cartesian coordinate system. So from here, from this diagram, you can easily find out r hat is sine theta. Sine theta is this cos phi, then you have x. Sine theta cos phi x hat. Sine theta sine phi sine theta sine phi is along the y direction, so sine theta sine phi y hat, plus cos theta is along the z direction, cos theta z hat. So if our unit vector can be represented in terms of x unit vector, y unit vector and z unit vector. So we can also do it for the theta unit vector. Theta unit vector, you know that is perpendicular to the r unit vector. So in this expression, you just need to replace theta by theta plus pi by 2, then you will get the expression for theta hat. So when I replace this theta by theta plus pi by 2 here, sine of theta plus pi by 2 is cos of theta, sine of theta plus pi by 2 is cos of theta, cos of theta plus pi by 2 is minus sine of theta. So this is the relation between the theta hat and the x hat, y hat and z hat. We can also find out the relation between the phi hat with the x, y, z unit vectors. For that, you first need to remember is phi is in the xy plane, so theta will become now pi by 2. In the xy plane, theta becomes pi by 2. Another thing is that phi is also perpendicular to the theta, so phi should be phi is equal to 5 plus pi by 2. So when you plug it in here, finally what you get is phi hat will be minus sine phi x hat plus cos phi y hat. If we write this in the matrix form, you can always convert the unit vectors in the spherical coordinates from the unit vectors in the Cartesian coordinate system by using this coordinate transformation matrix here. But what we are interested is in the coordinate transformation from the Cartesian to the spherical coordinates, spherical to the Cartesian coordinate system. What we have here is Cartesian to spherical. We want is just reverse. We want from spherical to Cartesian. So I can just take inverse of this, multiply with this is what I have. If I want to find relation between the x hat, y hat, z hat and r hat, theta hat and phi hat, I just take inverse of this coordinate transformation matrix. Then I will be getting it. So taking the inverse of matrix is a very tricky thing. It takes a lot of time, a lot of hard work. But here we have a cure here. So basically this coordinate transformation matrix is a unitary matrix. There is a property for the unitary matrix. We'll use it here. For any unitary matrix, when you multiply U with U transpose, it becomes identity matrix. So that means U transpose will become U inverse. So we don't need to find the inverse of this coordinate transformation matrix. We just take transpose of it. Then we get the relation between the x hat, y hat, z hat with r hat, theta hat and phi hat. So from here I can find the coordinate transformation from the spherical to the Cartesian. So we have done the preparation for the coordinate transformation to find the far fields of a vertical electric dipole. So let's look at the diagram for the vertical electric dipole. This XYZ system. We assume that this current carrying element, Hertz dipole, is oriented along the z-axis and its position at the origin of the coordinate system. Its length is dl, it's carrying a current of I naught. So now here, d unit vector was for any arbitrary oriented current carrying element Hertz dipole. But now here is along the z direction, so unit vector will be just replaced by z unit vector in the previous expression we have for the fields. So just replace d hat by z hat. This is what we have. This was d hat, we replace it by z hat. So now I want to analyze this in the spherical coordinate system because it's easier to find the fields in the spherical coordinate system and it's more convenient. So I want to replace the Cartesian coordinate z hat, unit vector z hat. I use the coordinate transformation. I can replace this by cos theta r hat minus sin theta hat. We have already done the derivation in the previous slide. So you do the cross product of r with this. Finally, what you are getting is sin theta phi hat. So the magnetic field is having variation with respect to theta as sin theta. So this will be helpful for drawing the radiation pattern method. You can easily find the electric field now. Once you have the magnetic field in the far field, you can find the electric field as eta times cross product of magnetic field with the radial unit vector. So when you do that, this is the expression you have here. So finally what you are observing is that in the far field of the vertical electric dipole, you just have theta component of the electric field and phi component of the magnetic field. They are perpendicular to the radial direction in which wave is propagating, and their variation with respect to theta is sine of theta. So we can plot it. Basically we can do the polar radiation pattern of a Hertz dipole, vertical electric dipole in the far field for any arbitrary phi is equal to constant. We make phi is equal to constant. Let's say maybe phi is equal to 0 or 90 degree or 45 degree. In that case, we can plot the fields, and because of that sine theta, this look like a shape of 8. So maximum radiation is at theta is equal to pi by 2. Sine of theta is maximum at theta is equal to pi by 2, and sine of 0 is 0. So along the theta is equal to 0, we don't have any radiation. That means along the z-axis, we don't have any radiation. We have all the radiation in the xy plane. Maximum radiation is in the xy plane. At theta is equal to 0, 0 radiation. At theta is equal to pi by 2, we have maximum radiation. We can also similarly find the fields for the horizontal electric dipole. For the horizontal electric dipole, let's consider it's y-directed. Let's consider a horizontal electric dipole position at origin, and it is of length dl and carrying a current of I naught. In that case, what should be the electric field and magnetic field for that? So here also similarly d hat should be replaced by y hat. D hat was for any arbitrary orientation of the dipole, but now this is oriented along the y direction, so y hat. So the expression simply becomes magnetic field will be, so we have this r hat cross product with y hat. So now I want to do the analysis in the spherical coordinate system, so I need to convert this y hat to spherical unit vectors. So I can simply do that. We have done the derivation for that. So now this is y hat in the spherical coordinate system. When I do cross product with the radial unit vector, what I'm getting is magnetic field is having phi and theta component. So we can get the electric field simply by multiplying with eta and doing the cross product of magnetic field with the radial unit vector, and we can also observe that electric field is also having theta and phi components for the horizontal electric dipole. So let us summarize what we have learned in this class. What we did was we started finding the electric field and magnetic field from the any arbitrarily oriented current density J. We derive it. It was a three-step process. First you find the magnetic vector potential, then find the magnetic field by taking curl of it. Find the electric field by taking curl of the magnetic field. So this was a three-step process. And once we have that, what we observed was the electric field and magnetic field often from this three-step process was having a very complicated expression, but most of the time we are interested in the far field of the antenna, so we just need to worry about the 1 by RD term in the expression, and it turns out to be the expression for electric field and magnetic field has only one term, both of them one term for electric field and one term for electromagnetic field. And one more observation was that in the far field, electric field and magnetic field was related. Electric field was having an amplitude which is eta times that of the magnetic field, and direction of electric field and magnetic field were perpendicular, and they were also perpendicular to the radial direction in which the wave was propagating. Then we have deduced the case of arbitrarily oriented Hertz dipole in the XYZ region, and from that we have again taken the particular case of horizontal electric dipole and vertical electric dipole. In the vertical electric dipole, we observed that field E was having only theta component and phi component for the magnetic field, but for the horizontal electric dipole, both electric field and magnetic field was having theta and phi component. Thank you. That's all for this class.